round, we're going to go through now. Everybody getting that? I think everybody got that. All right, so one of my colleagues in LabVIEW R&D, his name is Stephen Loftus-Mercer. He is the expert on errors in LabVIEW. I know about errors in LabVIEW. I have a lot of experience about errors in LabVIEW, but Stephen is the errors guy. So I just wanted to give him a shout out here because he helped me with a lot of the material for this presentation. He also designed the posters that you guys got today. All right, so stop saying error handling. Instead, figure out which one of these terms you actually mean. Do you actually mean error generation, error propagation, error response, error display, and error logging? Check it out, I didn't pull a Rick Perry, I remembered all 5 of them. So today we are going to talk about error generation and error propagation. Today we are not going to talk about response, display, and logging. Well, we are, but just for like a minute, okay? We're going to talk about these real quick, just so you can kind of get an idea of the 5 different pieces of error handling in LabVIEW. So error response. Error response, just real quick, if an error happens on your LabVIEW block diagram, what do you do about it? Do you ignore it? Do you retry something? Do you translate that error into another error for some reason? There is a lot of different ways to respond to an error on a block diagram. Thankfully, that poster that I gave every one of you when you walked in describes every possible way you can respond to an error. Since you already have a poster, I'm not going to spend any time in this presentation talking about this topic. So review the poster. Now, one thing I do need to say, though. To my knowledge, there are no mistakes on that poster. Unfortunately, that poster was designed 5 years ago. And when Stephen designed that poster, it was when LabVIEW 2013 was the current version. For those of you that are good on your LabVIEW trivia, you know that in LabVIEW 2014, we added an input to clear errors to let you clear a specific error. So on your poster, when it says clear a specific error or warning, the little screenshot there doesn't have this. But if we had designed the poster a year later, it would have that. So keep that in mind when you're looking at your poster. Poster's 5 years old, information's all still good, information's all still valid, but we do now have the ability to clear a specific error. All right, so that's a quick overview on error response. What about error display? So error display is when an error has happened and you need to get that information displayed to the end user somehow. You are almost always using simpleerrorhandler.vi or generalerrorhandler.vi to display that information to your user. Now, if you are not using those, that means you've probably got your own error display mechanism of some sort. And in that case, we've actually still got some really handy functionality on Simple Error Handler. In case you didn't know, you can actually wire an input of no dialog to that VI. And when you do that, it will not pop up a dialog. But what it will do is give you back a string that gives you the value of the message that would have been in the pop-up dialog. So if you're designing your own way to display error information for whatever reason, use this trick to get the string that we would be displaying in that dialog, and then display it however you decided to in your own custom error display mechanism. All right, then error logging. So error logging is what you do whenever an error occurs in the code and you need to log that somewhere. This is a huge topic. We spent an entire CLA summit about this topic one time. I'm not going to talk about this topic today. There are several error logging frameworks available online. You can just go Google and take a look at them. Just 2 quick things to keep in mind, though, when talking about error logging. You want to make sure that you log all the errors, even the ones that your code is handling, just so that you can make sure that your error, like you don't want there to be a problem with your error logger, right? One way to make sure there's not a problem with your error logger is to log everything. And then you can filter things out as appropriate. And in the case where there's no error, it's still a good idea to log, hey, no error happened. And again, that's so that you'll actually see some progress in there in terms of the timestamps. Okay, I can see that this time went on, there were no errors. So anyway, that's all I'm going to talk about in regards to error response. That's your poster. Error display, that's general error handler. And error logging, that's this stuff right here. I do want to mention LabVIEW NXG real quick. A lot of people don't realize that in LabVIEW NXG we've got a completely new error API. So if you think about current LabVIEW, you've got the simple error handler and general error handler, you've got error cluster from error code, you've got clear errors, and I think those 4 VIs are the only things that have to do with error stuff in the palette. There might be like one obscure one as well.
Merge errors.
What's that?
Merge errors.
Oh, okay, you're right, merge. So 5. Here we can see that the error API in LabVIEW NXG is quite a bit more expansive. We can see we've got a lot of VIs for just parsing the error cluster and learning information about it, modifying information like call chain and location and things like that. So when you're writing a new application in LabVIEW NXG, make sure you become familiar with this new error API because it is completely new and different from what's available in LabVIEW today. Also, I want to talk about warnings real quick. Yeah, don't use warnings. So a warning is an error cluster that has a non-zero code value, but the error Boolean is false. Okay. There are some APIs that generate warnings that are outside of your control. Like I'm pretty sure TCP has a few warnings that it generates. I know DACNX has a bunch of warnings that it generates. When you are writing your APIs and you are including error stuff in your APIs, don't do warnings because there's so many things that people do that assume an error is a value of true. Like they ignore an error cluster if the Boolean is false. That assumption is made across the LabVIEW spectrum. So once you start including warnings in your API, there's a good chance that people aren't going to see those warnings or they're not going to care about those warnings. So you need to use the error cluster to indicate an error condition or a no error condition, not this muddy area in between. All that being said, make sure your code is warning aware. So I see code that looks like this picture quite a bit. And I say, hey, wait a minute, what happened to your error wire there? It just ended. And somebody will say, well, it doesn't matter because that's the no error case, right? So if we hit that, there's no error and we can just go keep on our merry way. Well, if that wire coming into the case structure had a warning on it, that warning would be lost at that spot. Now, I'm telling you guys not to use warnings in your APIs. I'm not telling you to just blanket ignore all warnings. There might be some warning in some API that you are interested in, and how hard is it to just wire that error wire across? It's not that hard, and when you do, you'll maintain warning information on the error cluster. So try to avoid adding warnings to your APIs, but make sure your code is warning aware so that you don't lose them in the event that they are there. That's all I have to say about warnings. All right, so the meat of this presentation, error generation and error propagation. First, we're going to talk about error generation. This is when a block diagram generates an error cluster value that has a Boolean of true on its status. So we have generated an error. Something has gone wrong at a specific point in a block diagram. There are really only two ways that an error value can be generated on a block diagram. The first way is hopefully the most obvious way, and that is with built-in functions. The queue functions, the visa functions, call library nodes, the file IO functions, all of those things can generate an error cluster. So if you call the open create replace file function and you give it a bogus path and tell it to open that file, it'll return an error 7, right? File not found. The second way to generate an error is to actually have G code that you have written that generates an error value. And the two most common ways that that is done is with the error cluster from errorcode VI and the error ring. So you as the author of this VI have decided that something has happened to where you need to generate an error cluster value on that block diagram. So error cluster from error code is very common. We'll see it used a lot of the times next to call library nodes, because like a call to a DLL, if it returns a non-zero return value, then you might pass that into error cluster from error code to generate an error cluster value. So it's got an error in, and if you wire the error in to error cluster from error code, then and there is an error, then it doesn't do anything, it just passes the error out. So you want to make sure to always keep the error cluster from error code on the error chain so that if there's an incoming error, the function doesn't do anything and it passes that out. I tell people to always wire true to the call chain. It's very useful when debugging something to be able to know what point within the call chain of all the VIs the error occurred. Steven suggested that I point out that if you're on RT, adding the call chain can introduce jitter, so that's one reason you may want to turn that off. But most of the time, adding the call chain makes sense. And then whenever I use this VI, I almost always wire a string into the error message string input. And that's because that gives you an opportunity as the programmer of the code that owns this to give more information in the error cluster as to what happened. If you're just sending in an error code number and nothing else, it's not going to be as helpful for debugging the issue than if you can parse something on that diagram that gives you more information that you can then stick in the error cluster and say, like, a value of 7 was provided, but we expected a value of 6 or less, or something like that. That's something that you can stick in the error message to help whoever's debugging this go debugging.
Jared, doesn't that just write to the call chain like string?
So the question is, what does it do when you wire in an error message string? So you guys know an error cluster, right? It's got a Boolean, it's got a number, and it's got a string. Boolean's pretty straightforward, true or false, right? Number's pretty straightforward, that's your code. The string is actually really complex and nuanced. So the string in an error cluster can contain a lot of information. It's not just the call chain. It can contain information about the call chain of the VI. It can contain information about, it can contain the string that you provide here, which is the error message. There are other tags you can stick in that string that signify different things. So the source string in an error cluster is really complicated. And that's actually one of the reasons that I don't want people building the error cluster themselves. So I see code that looks like that a lot, where someone's not using error cluster from error code, someone's not using error ring, they're just taking an error cluster and bundling in the status, the code, and the source. There's several problems with that. One, you lose all of this nuanced information that may be stored in the source string when you would otherwise generate the error the correct way up there. Number two, what happens if I rename my Chromie VI to something else later? Well, now that string is stale, and that string doesn't even have the call chain information, so it's not very helpful for debugging. So unless you've got other restrictions, like you're on RT and you can't use VIs like this, do not build error clusters yourself. Build them either with error cluster from error code or with the error ring. So the error ring, yes, question?
Did your error message on 8 overwrite what's coming along?
So the question is, if you wire in the error message, does that overwrite something? No, that's the cool thing. So you are generating an error cluster with this VI right now. Remember, if you wire an error in to this VI doesn't do anything. It just passes the error out. So you're using this VI because you want to create an error value for some end user of this program. And in doing that, when you wire call chain true and you wire error message string, now the error cluster is going to provide the call chain and it's going to provide whatever additional information you wired into that string. Yes?
If you have an error out of a LabVIEW function that's already filled out the source string, what's your recommended approach for appending information like error messaging?
So the question is, what if you call a built-in function like a file IO primitive or something, and it returns an error? How can you provide more information into that error cluster other than what's already provided to you, which is the source string? So that would be a case where I think you're taking an error response, like on the posters, and you would be translating from the error that's given to a new error. And there's entries on the poster for how to do error translation. So that's what I would suggest there. I would say in that case, you're probably not using error cluster from error code. You're doing like some sort of translation mechanism. Question?
So when you do all this, you're still only going to see if there's no issue with being able to see only the first error that was generated if you have the cluster of multiple errors.
Right, so the question is, what about if multiple errors have occurred? In current LabVIEW, there's really no scheme for maintaining multiple errors along an error chain. The scheme is that you maintain the first error along the error chain. So if an error happened up here and another error happened over here, if you're doing your error propagation correctly, over here you're only going to see this first error. Now there's things we can do in NXG that I'm going to talk about later that enhance that procedure. But for now, in current LabVIEW, the best policy is make sure upstream errors are the ones that make it all the way to the end. Question?
Does the error cluster from error code, does it append that string only on an error condition, or does it append the string regardless?
So the question is, how does that VI act when there's no error condition? All right, so in that case, you would have an error coming in that's no error, and you would have an error code of 0. In that case, we do nothing to the error cluster. We output no error. All right, I'm going to move on to error ring. So the error ring is fantastic. I love this feature. I believe it was added around maybe 2012 or so. It is a way to generate an error value on a block diagram, similar to error cluster from error code, but it's got some really neat built-in functionality. I've tried to identify some of the cool things that it can do here on this slide. There are things like you can look at it, and from just looking at this on the block diagram, you can see whether it's an error warning. That's what the red X is. You can see if it includes the call chain, that's the little chain symbol. And you can see the beginning text of the error message that is going to be generated by this node. There's also some really cool things for adding format specifiers, which I'll talk about in a second. So when you're using an error ring and you want to generate a regular old LabVIEW error from the error ring, one example that I'll keep falling back on because it's easy and we all know about it is file not found. So you can drop down in the error ring and pick error 7, file not found. Most of the time I'm using an error ring, though, I'm using it for custom error codes. So one of the things that you guys are going to want to do is when you're using an error ring, you're going to want to make sure to, if you're doing a custom error code, which again I think is the usual use case for this thing, you're going to want to use one of the ranges that is defined in LabVIEW as being for not NI errors. So there's a ton of error ranges defined for errors in LabVIEW for DACMX, for Visa, for File I/O, for TCP, for queues, for notifiers, for semaphores, for rendezvous. All the APIs have a defined range for what errors they can generate. Okay? National Instruments is making a contract with LabVIEW users that those 3 ranges right there we will never use for anything that comes with an NI product. Those are ranges that are specifically for y'all to use in your APIs when you're generating errors. So figure out what range you want. The one that's 500,000, that's the biggest range in terms of the number of values it has. It's got 100,000 values. And then use that range of errors for when you use error rings and other ways to generate your errors. And then I'm not going to talk about error code text files too much in this presentation, only to mention that if you want to distribute your range of errors along with your application so that it does cool things like when you call general error handler, it pops it up and shows your error code with your message that you've defined. You can use error code text files to do that, and that's a feature that's in LabVIEW that you can launch from the edit error codes tool. Question?
Well, actually, to add to this, if you're developing a tool network, you get a custom error range code that's specifically defined for you and your company to use.
That's true. That's a good point, David. So David was mentioning that if you do provide products for the LabVIEW Tools Network, you're working with NI for to get those products published, and NI will actually give you your own special range that's not part of these, but that's just for your product. It's going to be on the Tools Network. Question?
Yeah, with the error ring, it's willing to nag one of your key links to allow us to distribute the work.
I'm about to tell you how to do that. Give me another couple slides. All right, so this is what my code typically looks like when I use the error ring. It looks exactly like what you see here. Notice the first thing is that I've got the error ring inside of a case structure. So if you don't need to generate the error value, in other words, if your code is running fine and the error didn't happen, don't call the error ring, because the error ring actually executes some code, it calculates a call chain, it does some other stuff that performance-wise you don't need to do that if you don't need the error value in the first place. So make sure you're only calling the error ring if you need that error value that it's giving. Also notice that I'm merging the error ring. So if there's upstream error, again, like I mentioned before, I want to make sure that that's the error that makes it to the end, not the value generated by the error ring. So notice that I'm merging the error ring in there. And then this is my favorite part about the error ring. This is the reason I love this feature is because of the little percent format specifiers. So check that out. Over there on the right, I've got my custom error code, which falls into the range that I talked about before. And then I've got a message. The specified operation on the specified file is invalid. Now, if I had just provided that sentence as my error message, and someone was using my application, and general error handler popped up and said, the specified operation on the specified file is invalid, you would ask, what the hell was the operation and what the hell was the file? That's what you would ask. That error message doesn't really help you. I mean, it tells you something went wrong, but that's all it does. And so with the error ring and these format specifiers, we can actually give you information. Look, I've got file %s, operation %s, and those two %s's add those two inputs to the error ring. And now I can pass that information when I generate the error cluster. Now, when somebody runs my code and that error dialog pops up, specified operation on specified file is invalid, it tells me what the file was and it tells me what the operation was, and that makes it a lot easier for me to debug. So try to provide that helpful information in those error values that you, as the G programmer, are adding on the block diagram when something goes wrong. All right, so when you use the error ring, check the little box to include the call chain. Always helps with debugging, unless you've got some other constraint why you can't. This one's for you. If you right-click on the error ring and choose Visible Items and deselect Error Explanation Text, it hides that whole sentence that we show, and it compacts the node down to be super tiny. So if you want to conserve some diagram space with the error ring, do that. And then here's just kind of a best practice. So when I've got a large application, I've got lots of custom errors that I'm probably writing G code to generate. And it can sometimes be really helpful for me to know what are all the possible places in my code where I might generate this error. Well, if I've dropped error rings everywhere, I mean, error rings are cool, like I talked about before, but when it comes time for me to go sort of parse my code and understand which parts of my code can generate this error, if it's just a bunch of naked error rings sitting everywhere, that's actually kind of hard to find. Like, you can't really do a text search for the stuff that's stored inside the error ring, so maybe I'll do a search for error ring, but now I'm seeing all my error rings, so that's not really that helpful. So what I do is I'll take the error rings and I'll wrap them in sub-VIs. So my error for module not synced. So I'll make a VI called module not synced -- error, just as a naming convention for myself. And now if I need to go explore my application to figure out where are all the places, like let's say this error happened, right? I'm running my app, I'm trying to debug it, this error happened. The first thing I'm going to do is I'm going to say, where are all the places where I might generate the module not synced error? Now, I'm probably also reading a call chain, so that's probably helping me find the specific spot. But maybe for whatever reason, I need to know where all the places are that I might generate this specific error. It's really handy to have this error ring wrapped in a sub-VI, because then I can just go look for where that sub-VI is, and I'll know all the places where I generate that error. You can also use bookmarks, that's true.
Control F and 5002 to find it.
Will it work when it's the code inside of an error ring?
I don't know.
I'm not sure if it will. That's why this sub-VI approach has been one of the easier approaches I've had. Also, if I can look for an object like a sub-VI, I prefer to do that over looking for text. Because when I start searching for like the bookmarks, like what if that's a bookmark I used in a bunch of other places? Whereas this sub-VI has one exact thing that it means. So, there's multiple approaches for sure. All right, that was everything about error generation. You guys are using error cluster from error code, or you are using error rings. You are not bundling the error cluster yourselves, and you're following the best practices that I talked about for those two VI, for the VI and for error ring. So now we're going to talk about error propagation. So when an error happens, we need to get it through the code somehow, right? There are many different aspects to error propagation. So LabVIEW is a parallel programming language, one of the reasons we love it so much. But that means you might have parallel error paths going in your code. So you need to manage that and maybe a lot of times merge them into one, right? Sometimes when an error happens, you may want to skip the execution of some nodes. So you'll propagate the error and probably have a case structure. Lots of tools for doing that propagation, merge errors, case structure, shift registers. But there is one, and only one, overarching rule when it comes to error propagation. Don't break the error chain. Do not break the error chain. Don't break the error chain. So we can see down here I've got a sequence of VIs that are doing stuff with databases, right? If I dig into those VIs, there might be more hierarchy of sub-VIs inside of them. We're talking about like probably a pretty complex application. So pick any random sub-VI in here. Let's pick this one right here. So that sub-VI has an error in and an error out. And that sub-VI has faith in a higher power. That higher power is you. That sub-VI has faith that whatever happens, error, no error. If there's an error, you are going to make sure that that error is shepherded to its final resting place. Its final resting place might be simple error handler VI. It might be your error logger. It might be an error indicator on the front panel. That sub-VI doesn't care. What it cares about is that the higher power, which is you, gets that error to its final resting place. Now, all it takes is one place where you, the higher power, break the error chain. One place where an error goes into something and that error does not come out of that thing. That sub-VI's error that it generated is now lost forever. Well, probably not forever, because you're going to have to go debug why something is going wrong, but you're not being told about it. The only thing worse than an error happening and finding out about it is an error happening and you not finding out about it. Those are super hard to debug. And anytime you break the error chain, that's going to be the hard thing you have to debug. So, this is probably the most important part of the presentation. I'm going to go through the different ways that we can break the error chain and how we can try to avoid it. The first way that we can break the error chain is the most obvious way that we can break the error chain, which is not wiring the error through things. Okay? So here's some code that's doing some DAC. we can look at this diagram and very easily see where the error chain is broken. When you've got 1,000 VIs and hierarchies that go 10 or 12 sub-VIs deep, and the error chain is broken somewhere in there, you're not going to see it as fast as you see that. You're going to spend a lot of time trying to figure out where that error chain got broken. People have heard me talk about train tracks and how I don't like it when people just brainlessly add an error in and error out on a VI, particularly class VIs, when the VI is actually not doing anything with the errors. This is one of the reasons, is because when you get to that point where you need to debug and try to find where the error chain is broken, every VI that has an error in and error out is a possible culprit in breaking the error chain. So if your VI doesn't need error in and error out, don't put them on there, because that makes things easier for you when it comes time to debug, when you want your code to run more parallel, etc. So there are a few tests in the VI analyzer that can help fix or help detect this issue. One of those tests is the unused code test. So the unused code test, a lot of people think, oh, well, that's just going to find like an add primitive that doesn't have its output wired or something. It will find that. It'll also find cases where you take a value, wire it to a loop border, and then don't do anything with that value, which is exactly what's happening in this screenshot here. So the unused code test in the VI analyzer would detect this. The more obvious thing that the VI analyzer can detect is with the error cluster wire test. So if there's any function on your block diagram that has an error output but you haven't wired it, that test will detect that issue as well. So we've got a few VI analyzer tests that can help us detect these issues where the error chain is broken. Also, if you like automatic error handling, I'm surprised you're in here right now. Nevertheless, automatic error handling can sometimes detect this issue as well, simply because you've got a function, like a file IO function. If its error's not wired, auto error handling is turned on, it'll pop up a dialog. Auto error handling won't find what's in this screenshot right here, because that's not a function terminal, that's not wired, that's a tunnel. And auto error handling doesn't care about those. So anyway, just a few ways to be able to detect the error chain being broken. I highly recommend using these two VI analyzer tests. If you get into that situation where an error is happening and you're not told about it, and you start going down this path of trying to find out where the error chain is broken, step one, run those analyzer tests and see what they can find. This is one of my issues that I want to tell the world about, and that is zero iteration for loops. So here we have a for loop that's doing some TDMS stuff. And let's say there's an error coming in on that error wire to the for loop. Let's also say that that 2D array going into the for loop is empty. What that means is that the for loop is going to run 0 times. And what that means is that the error tunnel coming out of the for loop is going to have no error on it. This is a huge question that comes up on the NI forums all the time with newer LabVIEW users. And it's something that I think requires just more instruction and more communication for people to recognize what happens with a for loop when it runs 0 times. Have you guys ever heard the term default values? So you know what default values are, right? It's like you've got a numeric on your front panel and you can set its default value to 0 or 5 or 10 or whatever. So when someone opens the front panel, it's always got that default value. When you hit the phrase default values, which is a term we use in LabVIEW R&D, it basically means for a data type, what is the default value for that data type? So for a Boolean, it would be false. For numeric, it would be 0. For string, it would be empty string. For error cluster, it's false, 0, empty string inside the cluster. So when that for loop runs 0 times, all of the output tunnels are going to return default values, which for the ref num is going to be just null ref num, and for that error cluster, it's going to be false, 0, empty string. So if an error went into that for loop, you are not going to see it on the output of that for loop, and that is another way that we might break the error chain without realizing it. The most common way to address this, which is what we have to tell people on the NI forums every time this issue comes up, is that you replace those tunnels with shift registers. So when you stick shift registers on a for loop and the for loop runs 0 times, that is just kind of like a semantic realism, for lack of a better term, that whatever got passed in on the left is going to be output on the right. So if we turned those tunnels into shift registers and an error came into the for loop and the for loop ran 0 times, whatever we passed in on the left is going to go out on the right. So that's how we would fix this issue so that we didn't lose the error on 0 iterations. Yes?
Sometimes when I've seen people break the error chain, it's because they're concerned that if there's an error coming in, that a function like the TDMS file close that should always execute whether there's an error or not, maybe it won't execute.
Uh-huh.
And so then they're concerned that, well, I don't want to wire the error into that function, and therefore they break it. So do you have any insights into how you can tell which methods will still execute even if an error is passed in, or with NGX if they'll indicate that?
Right, so the question was, sometimes people break the error chain because they are unclear about the behavior of functions on incoming errors. The vast majority of functions in LabVIEW, if they have an incoming error, will no op. They won't do anything, they'll pass the error out on the other side. List folder. If list folder gets an error in, it's not going to list your folder, it's going to return empty strings for the folder names, and it's going to return the same error out. But there are some functions that do operate, regardless of what the incoming error value is. TDMS closed is an example, and we've got one right here on this diagram here. So a function that has an error input, but it's still going to do its thing. Currently, the way that you tell the difference is the documentation of the function. If you right-click and do help, documentation comes up. The error out parameter or the error in parameter will tell you this function operates. This function will, I forget the wording, but it'll either say something like this function will operate normally on incoming error, or this function will operate regardless of what the error is, or whatever it is. I think it's like standard error in behavior or something like that. So right now, there's really no way to visually, just by looking at a diagram, know whether a node functions in method number 1 or method number 2.
By and large, all the closing of references.
By and large, like as a general rule, if it's closing something, it's going to operate regardless of incoming error. Unfortunately, there are a few exceptions. They're documented. To my knowledge, the NXG team is researching ways to make that more obvious. In current LabVIEW right now, you got to read the documentation, or you just got to kind of go with the best practice of if it's a closed function, it's probably going to operate even on incoming error. All right, so so we've got a new test in the VI Analyzer toolkit in LabVIEW 2018 that will detect this situation. The situation has bothered me for so long, we finally got a new test in there. If you've got code that does not handle error tunnels appropriately for for loops, it'll be detected by the for loop error handling test in the VI Analyzer in 2018. So this is yet another way the VI Analyzer can help us find places where we've broken the error chain. Basically, I want to tell the world the blue text up there. Every single time you implement a for loop on your block diagram, ask yourself 2 questions. The first question you need to ask yourself, is there any possible way this for loop can run 0 times? And if the answer to that question is yes, answer yourself the second question. What will this for loop do if it runs 0 times? Will it handle errors appropriately? Will it handle references appropriately? Because that reference wire should be a shift register as well, because you want future code to be able to operate on a valid reference. And it will be a null reference if the loop runs 0 times. So every time you'll drop a for loop, first question, will this run 0 times? Second question, am I handling the 0 iteration case correctly? Please start asking yourself that every time you drop a for loop.
Darren,
Yes?
is there any harm in just sticking shift registers and references and errors for every single for loop?
So the question is there any harm in sticking shift registers on the ref num, shift register on the error cluster? Generally no, except for the scenario I'm about to describe in the next slide, which is, what if you want your loop iterations to run independently? So your loop's going to run 10 times. If it errors out on iteration 4, you still want iterations 5, 6, 7, 8, 9 to do something. In that case, you can't use the shift register, because as soon as the error goes in to the right, only the error is ever going to come out on the left again. So in the case where you want your iterations to run independently regardless of error, your code needs to look like this picture up here. So you can see we're using a shift register for the ref num so that we don't screw that part up. But then for the errors, we're still using tunnels, but we're building up the errors on the end so that every iteration can run and have a chance to do its thing regardless of what happened on a previous iteration. We can't use a shift register, like I said, because the error generated would screw up future iterations. So instead, we build up the errors on the loop border. I have yet to run into a case where somebody did this and ended up having a performance issue, and that's because I have yet to run into a case where somebody wanted this loop to run 1,000,000 times. Usually in these situations, your loop's going to run a small number of times. If there's the chance that your for loop is going to run a whole bunch of times, you need to be concerned about building up those errors on the loop border, because now you've got an array of error clusters, And if there's 10 of them, no big deal. If there's a million of them, kind of a big deal. So watch out for high iteration counts. Question?
What, let's say if I have my loop that is going to run, I don't know, 1,000 times, what is more efficient time-wise? Put a shift register on the error or a conditional to stop the loop if it detects?
Okay, so good, yeah. So the question is, what if we do know that the loop is going to run a whole bunch of times? If you don't care about, if you don't care that future iterations run if an error occurs, then a shift register is fine. If you do want as many iterations to run as possible, you would need to take this approach, and if you're concerned about it running a whole bunch of times, you could still stop, but then you wouldn't get future iterations running because you would stop the loop. So it all depends on if you want all the iterations to run regardless of error. As soon as there's an error, then yeah, go ahead and stop the loop and just whack to the conditional. Question?
What if you turn that indexing tunnel into conditional indexing? You wire the error cluster into the question mark and like you can in the case structure?
So the question is, can you wire, on conditional terminals on a for loop output, can you wire the error cluster to the condition? The answer is no. You would have to unbundle the status and wire that in. You can only wire booleans to that.
So that would help you with the million.
That would allow you to only add errors to the tunnel. That's right. That's a good point. All right. So notice the merge errors that happens after the for loop. The reason that's there is because if an error happened before the for loop executes, and the for loop runs 0 times, you will lose the previous error that happened unless you merge it in. That's why that's there. In case the loop iterates 0 times. These darn 0 iteration for loops. All right, so here's another new feature in LiveView 2018. It's called an error register. So basically, the feedback we got at NI is that people got tired of having to write code that looks like that for parallel for loops. That's not a parallel for loop, but pretend that it is. You can't have an error shift register on a parallel for loop. Your code will be broken. You can't have an error shift register. You have to build up errors on the tunnel. So people got tired of having to make that code where you build them up on the tunnel, then drop the merge, and wire the error around. This is effectively exactly the same thing. So now in LiveView 2018 and later, if you have error tunnels on a parallel for loop and you try to convert them to shift registers, you'll get error registers instead. And this code is functionally identical to this code. It just looks nicer and it's quicker to write.
Is it only for parallel for loops?
Only for parallel for loops, that's right. So the iterations can still run in parallel, just like from before, but those errors get merged up and then combined in a nice way for you behind the scenes on the output. So yeah, you can, and you don't have to do anything special to create these. Just right-click on the error tunnels. And I think we did actually change the wording of the right-click menu to convert to error register. I don't remember offhand, but either way, they just get made automatically for you, and now you get that functionality for free. Quiz time. Somebody tell me what's wrong with the error propagation in this VI. Hint: there is something wrong with the error propagation in this VI. Costa knows, but he doesn't count. What's the question? What was the one?
2 sources.
There's 2 sources. That's okay. I mean, we can have parallel paths executing. It's fine for that sub VI at the top to execute in parallel with the code down there.
An error generated in this will be propagated versus one generated further up.
There you go. So the problem is with that merge errors over there. See our error in? Follow the error in. Everything's looking great. Goes through the notifier function, goes through the event function, notifier, close. It's the top input on the merge error inside the case structure, but look, it's the bottom input of the merge error outside of the case structure. What that means is when this VI runs, if there is an error in to this VI and that sub VI up there generates an error, which one is going to get output by this VI? The one by the sub VI. But that's not what we want. Remember, we want upstream errors to be propagated all the way through our code. So another way to break the error chain is with sloppy ordering on merge errors. So this code is correct. And all I did was switch the order on the merge errors on the very, very far right. So now we're still merging the error from the sub VI up here, but if an error happened before this code ran, that's the one that's going to win on the merge errors on the right, because whatever's up closer to the top of the merge errors is what ends up coming out on the other side. So watch out for sloppy merge errors ordering. To summarize, oh, question.
Why don't they make it just merge errors item that you can't
So the question is, could we restrict the editor gesture on the merge errors so that you can only expand on the bottom on the top? That would probably bother me at some point. I think there would probably be some point where I wanted to make it move up for whatever reason. Maybe, hold on now. What if I've got the G code on my diagram that's merging some errors, and then I've got the error input that I want to wire into the top of it? Then I'd want to expand up and wire the error control over to it. Don't restrict my editor, man. Question?
Can you control, click, switch, like channel?
So the question is, can you do the little switcheroo thing where you hold down control and click on the merge errors? You can. You can do that on any function that only has 2 inputs. Once you add a third input, you can't do it.
What do you think wire the error output in the source string?
I'm going to talk about that in a minute. The question was, why didn't I wire the error output on the format into string? And that just so happens to be something I talk about in a few minutes. All right, so to summarize the most important part of this presentation, run tests from the VI Analyzer toolkit to help you find places where the error chain might be broken. Error cluster wired is a good one. It'll detect those functions that don't have their outputs wired. And it also provides options to ignore certain objects. I almost never wire the output of the delete function. So if there's a file on disk that I want to delete, I'll call the delete function. Maybe it gets deleted, maybe it doesn't. I don't really care. I tried my best. I move on. I don't check the error output of that function. That's one of many examples, and the test provides options to ignore some of those that are frequently unwired.
But.
No, Costa. No. Yeah, that's right. Okay. Costa is one of my colleagues at National Instruments. He and I have different opinions on what I just said out loud. Another test to avoid is another test to run is unused code. That's going to find places where, like that thing I showed in the DAC VI, where the error went to the tunnel but then it didn't go anywhere. That test will find that. The for loop error handling test in LabVIEW 2018 and later will detect those 0 iteration loop situations where you might lose errors. And so Stephen Loftus-Mercer is my colleague in LabVIEW R&D, as I mentioned before. He was invaluable in helping me put this presentation together. He loves automatic error handling. I hate automatic error handling. However, with your wife, you pick your battles. Well, Stephen's kind of like my work husband, and so I pick my battles with him. And the battle I chose not to pick was, he asked me to add this bullet in this presentation. So one possible way that you, if you are not me, could try to find ways that the error chain is broken is by turning on automatic error handling. But there's a few assumptions with that. First of all, one assumption is the error condition that it would detect actually ends up happening when you're testing, which isn't always the case. Your code may run without errors when you're trying to figure it out, and may run with errors later on once it's out there in the world. So another thing is that assuming you only want to run it during development, that means you need to add some tooling to your process where you turn it on for everything while you're debugging and testing, and then you turn it off for everything once you're ready to deploy your code. So that's Stephen's bullet right there. Take it with a grain of salt. All right, so this is something I mentioned before that I was going to bring up again. Another note in LabVIEW NXG, a really cool feature that we have is the ability to multiplex errors on an error cluster wire. So this is really, really neat. We do not have this in LabVIEW, but we do have this in LabVIEW NXG. So check it out. I've got a file function, a TCP function, and a data type parsing function. And every one of them is doing something stupid. So every one of them is generating an error. Now check it out. I take all 3 of their errors and wire them into this new VI in NXG called multiplex errors. Notice that VI has a single error cluster output. So on a single error cluster wire, we have now stuck 3 errors worth of information on that wire. And so now notice, I then take that wire and I wire it down into demultiplex errors. That gives me an array of errors that I can then pull out and check it out. Every single one of those errors is shown here. That was stored in that single error wire that went into demultiplex. Also, notice the display error VI. That's the NXG equivalent of simple error handler. And that will pop up a dialog that lists all 3 errors. So even though it's a single error cluster wire, we can store multiple errors on that wire. So it's a really cool, neat thing that we have in LabVIEW NXG that we don't have in LabVIEW.
They're going to backport it?
The plan is not to backport it to LabVIEW. So this is an NXG only feature for now. What's that?
Sorcery.
Yeah, isn't it cool? Question?
Is that an
So the question is multiplex errors expandable? It's not, but the fourth input you don't see is an array of errors. So if you had more than 3 errors you wanted to multiplex, just drop a build array down and you can wire them in. Was there another question over here? Yes?
Yes, it doesn't know how many errors. I guess it's down to 3. Would it know how big the array is?
Oh, so demultiplex just returns an array. I know there's 3, so I indexed out 3. If I had indexed a 4th, it would just be no error because there wasn't a 4th error. You could do array size and figure out how many are in there. Is there another question? Nope. All right. So anyway, just a cool thing about enhanced error functionality in NXG. All right. So I'm sure some of you have heard me pontificate about this topic before. I really don't like how we have all fallen into the habit of wrapping every single one of our sub-VIs with an error case structure. It was a best practice there for a while. All of us just did it, like back in the early 2000s, right? Early mid 2000s, late 2000s. Oh yeah, I got a sub-VI. Let me wrap its diagram with an error case structure. I'm trying to get us all to change that because I think it's a waste of time. I think it's a waste of block diagram space. Because if we take this diagram and we remove the case structure, we get this. Now let's look at this. There's 3 functions right there. Those are all file IO functions. We can safely assume that all of those no-op if they have an incoming error. So that means every one of them is returning an empty array. That means the for loop is going to run 0 times. That means an empty array is going to come out of the for loop. Empty array is going to come out of that other output. And the error out is just going to match the error in. So that VI is going to function exactly like we want it to on an incoming error. So why are we bothering to waste time creating the error case structure around this diagram? We don't need to do that. We're wasting our time. We're wasting our block diagram space. With rare exception, functions like these are always just going to skip execution and pass the error into the error out. So with that behavior being the case, we really don't need to tell LabVIEW, no, really, don't do anything if there's an error, because LabVIEW's already not going to do anything if there's an error. All right, so there are 3 instances where you do want the error cases, and all 3 of them are rare. The first one is the least rare, which is you have G code that is somehow manipulating the error stream. In other words, you're doing something that's on one of those posters. In those cases, it makes sense to use an error case structure because you don't want to mess with an error stream when there's an error coming in. You only want to mess with the error stream if your G code has decided, oh, there's something I need to do about the error. The other 2 cases are really rare. I hardly ever see them. If your code needs to output non-defaults in an error case, for whatever reason, use an error case structure. If your code is going to run for 1 billion hours, regardless of the error, well, you probably want to case that out so it doesn't run for 1 billion hours. Whenever you do wrap your code in an error case structure, add a comment explaining why. So here's an example of the first bullet. We are manipulating the error stream of G code. We've got a VI that's doing something on a database, and an expected error might occur. Error 8146 is something that we know what it means. It means that the database is invalid. We're actually okay with that. Our whole app doesn't need to shut down if the database is invalid. We're just going to return an empty array of contacts. So, yeah, an empty contact value. So in this code, we're going to clear that 8146. Well, I've got the comment there that says, if error 8146 occurs, blah, 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 we're fine. But I don't want this code to clear an 8146 that's coming in from upstream, because that would mean something different. That is not the 8146 I'm expecting if it's coming in from upstream. So in that case, we wrap the code in an error case structure because we don't want to mess with something that has happened upstream. So that's an example of when you would want to use an error case structure. Question?
What about performance that, for example, you are running on a high-speed application, really high-speed application, and if you have 5, 10 VIs in your sub-VI, you're going to call each one of them.
Right.
Is that going to affect your performance or not?
So the question is, what about performance? What are our performance concerns? If we're in an error condition, I don't think we usually care about performance. If we're in a no error condition, then our code's actually going to run faster without the error case structures. So this is something that Steven has taught me. Anytime you've got a decision point on a LabVIEW block diagram, a case structure, an event structure, a select primitive, anytime you have a decision point, there are all sorts of optimizations in the LabVIEW compiler that we cannot do. So if you've got a block diagram and there's no decision points, it's just straight up logic with no case structures, no selects, no anything, there's just a wealth of optimizations that the LabVIEW compiler can do that get thrown out whenever there is a decision point. So every one of your block diagrams that has an error case structure around its contents, you're losing potential optimizations because of that case structure. Yet another reason to get rid of case structures if you don't need them. Cleans up your block diagram and in some cases improves performance. Questions?
Are these going to be leaving from the class templates and everything?
So the question is the LabVIEW class templates, whenever you make a new access or a new method or whatever, they have a case structure. So there's a story behind that too. We wanted there to be another option in the dialog when you make a new accessor or a new method that says create it without the case structure. And there's already so many options in that dialog. We got pushback. We're like, no more options. Just leave it there. So it's easier to remove it than it is to add it, is basically the logic. So if you don't want a case structure in your method VI, just right-click and do remove structure, or control space, control shift R will also remove it. But that's kind of the logic behind why those are still there.
What about if you're coding your VI doesn't have error propagation, doesn't have code that has error clusters?
So if you have a VI that doesn't have code that does anything with errors, I would say remove the error in and error out off of the VI. All right, so this is coming over to the question I got about the formatting string earlier. There are a lot of functions in LabVIEW that have error terminals. A lot of functions with error terminals. Do we need to wire every single one of the error outputs on every single one of these functions? You guys probably know what I'm going to say. I'm going to say no. So if there's a function that cannot reasonably error out, do not bother wiring its error output. For example, this format into string. There is one error this could return, and that is memory is full. If this runs and my memory is full, I've got other things to worry about than this format into string. So this is a good example of a case where we do not need to wire the error output of a function. These are functions also, like I mentioned before, that I never wire the error output on. And try to delete the file, try to close the reference. I don't care if you can't delete the file or close the reference, I got other stuff to do. So don't worry about the error. I mentioned the error cluster wire test in the analyzer before. It has options to ignore some of these types of functions. In fact, all three functions on this slide are functions you can ignore on that test. So if you're like me and you're okay with having those error outputs unwired on those functions, you can configure this test to ignore those. All right, so just another quick note about auto error handling. I am not a fan of auto error handling. I feel like you, as the owner of the block diagram, should wire the terminals you care about. You should ignore the ones you don't. And your editor shouldn't be popping up dialogues if you haven't asked it to pop up. So I turn off this option so that auto error handling is not turned on any of my new VIs. There's a VI analyzer test you can grab online that you can point to your entire application, and it'll turn this setting off on everything. I think it looks ugly whenever somebody just drops a clear errors or like an empty flat sequence and just wires the error to it as a way to tell the LabVIEW editor that they are ignoring that error. My personal preference is to not wire that error, and that way you know you're ignoring the error. I have a presentation called Brainless LabVIEW, in case any of you have not seen it before. It's at bit.ly/brainlesslabview. I pontificate about all this stuff and more. Auto error handling is one of the things I pontificate about. There's also a video of it there too, thanks to Mark. So you can go to that link and either read through my slides or download or go to YouTube and watch the video. All right, my closing thoughts as NI Week 2018 is winding down. 4 minutes to go until the entire thing is done. I'll let you at 4:01 they come in here and start taking chairs. Every error wire on your block diagram, you should be making a conscious decision about. You should be thinking about. Do not brainlessly wire errors across your diagram, but think about how the error is being propagated on this block diagram, how errors are being generated on your block diagram. You should be able to glance at a diagram and instantly know how that diagram functions in regards to errors. And the two ways you should know that are the patterns that I provided in this presentation should be immediately obvious when a diagram comes up, and when there's exceptions to things, like the error case structure I talked about before, there should be commentary describing, here's why we have an error case structure, or here's why we don't care about the error coming out of this function. Code should be documented well. The problem with auto error handling that I have is that there's no way to know if your code's going to pop up dialogues. That's the main reason I don't like it. You got to go into VI properties and see, is it turned on, is it turned off, or usually what ends up happening is you run the code and dialogues pop up. So that's one of the main reasons I don't like it. It's not explicit error propagation and error generation. It's implicit and it's harder to understand by looking at the code. I want to be able to look at a block diagram and have no question about how the VI functions. And without error handling, I can't do that. The number one thing you should take away from this presentation, though, is that the error chain should be immediately obvious on every single diagram. You should see the functions wired together with the errors that you care about. There should never be any ambiguity about for loops and how many times they run. There should never be any ambiguity about the order in which things go into merge errors. Error in, error out, make sure there's a constant chain between them. If there's parallel code, make sure things are getting merged in proper order. That is all I have. Thank you very much, everybody. Make sure to grab a poster if you haven't already.